Hello guys. So welcome back to the second round of Varun versus Varun. So this time the tables have turned. Just a little bit introduction about ourselves again. So I am a 2018 graduate from Delhi Technological University, and I've been working with Amazon for the last 2 years. I That was my first job that I got, and I have been at Amazon only ever since. So Varun, you want to give us a quick introduction about yourself?
Sure. So, hi everyone. I am Varun. I graduated from NSIT, and after that, I have been working in like multiple companies. And recently, I like did my master's from University of Wisconsin at Madison. So, like we have been recording some videos in the past. So, I really look forward to this video. I hope I am. So this time, since I am the one who is being asked the question, I hope I'm able to solve the problem till the end.
Okay. So tell me, do you know what a binary tree is?
Yes.
So can you quickly walk me through the definition of a binary tree?
Okay, so basically binary tree is like it's a data structure which has a property where each node has some data in it and it has a left child and a right child, and this property is maintained recursively. Basically, like each node is further a binary tree. So it's a tree
Mm-hmm.
kind of a structure going top down or
Okay.
bottom up, whatever you call it.
And okay. So is it necessary that each node should have a left child and a right child?
No, like there is a provision to have a left child and a right child. You can have no childs as well, but there will be two children since it's a binary tree.
Okay, got it. And I've heard that there is something called as a binary search tree, which are some special
Oh.
kind of binary trees. Do you know what are those?
Yeah. So basically, a BST is like it's basically a ordered kind of BS. A BST is like a ordered binary tree in such a way that the left node is always smaller than the root node, and the right node is always greater than the root node. And this property is again maintained recursively. Hello, I
Am I
lost you.
audible?
Yeah, now you are. Yeah.
Okay.
You got the definition right? What I said.
Yeah, I
Okay.
got that. So
Okay.
looks like my connection is not stable. Sorry
Okay.
for that. But
No
yeah,
problem.
let's continue.
Okay.
So the problem goes something like this, that you are given a BST,
Okay.
okay, and a target number.
Okay.
So now you have to search, you have to find whether a pair exists in this BST
Okay.
whose sum will be equal to the target number. So basically, I'll give you a BST and I'll give you a target number. You have to go through that BST and try to find out if there is any pair, basically any two distinct nodes, the sum of whose values will be equal to your target number.
Okay.
And
Got it.
for the time being, we don't want the nodes themselves. Just return true false, denoting whether such a pair exists or not. So for
Okay.
better clarification, I'll try to give you an example. Give me one thing, 1 second.
Yeah.
Uh, Let me know when you see the photo.
Yeah, I can see it.
Okay. So as here you can see, we have a BST of 7 nodes, 1, 2, 3, 4, 5, 6, 7. So
Oh,
let's
sorry.
say,
Sorry.
oh,
I pressed
okay,
enter
let
and it
me,
got deleted. Yeah.
okay,
Okay.
got it back. So yeah, so let's say I give you the target of 8. So you need to return true because we can clearly see that there are two nodes 3 and 5 whose sum will be 8. There is
Yeah.
another pair also 2 comma 6 whose sum will be equal to 8. Then let's say if I give you a target of 20, you need to return false because there is no
Oh,
such pair whose sum will be equal to 20.
yeah.
And one other thing is that you can't consider the same node twice. Like you can't consider that 4 plus 4 is 8 because 4 is present only once.
Oh, okay. Okay.
So I'll just repeat again that I don't want the pairs themselves. You just need to tell me true or false.
Okay. Got it. Uh, so like the naive approach that's coming to my mind is that
Hmm.
like just traverse and store the tree somehow and then like pick up every pair. But that's order n square. I don't think that's a very good approach. So yeah, okay. So like we can break it down to a problem that I have like some experience with. So for example, so you are given a tree, right? In the BST, like we can just like store the tree in an array, in a sorted array. And once we have the
Okay.
sorted array, like we can use this like this 2-pointer approach kind of a thing, like where we have a left pointer on the leftmost node and the right pointer on the rightmost node, right? And then
Okay.
what we do is like we just sum the values at these nodes and decide where we have to go. Like for example, in this case, let's say that we got 1, 2, 3, 4, 5, 6, 7 inside the sorted array. We pick 1
Okay.
and we pick 7. And our target is, say, for example, 6. Let's go with 6 right now. So we know that 1
Okay.
plus 7 is 8, which is greater than 6. Then I know that my answer can never include this highest value on the right, which is 7. So I'll move to the left
Okay.
from 7. So I'll come to
Okay.
6. So now I'll compare 1 plus 6.
Okay.
This is again greater than 6. So I move to the left. So to the left is 5. Now I again compare 1 plus 5. So I found the answer. Similarly, like we can move left and right and then get that answer. And this will be like
Okay.
an order n kind of thing because like we are traversing in the sorted array.
Okay. So before this, you had suggested some brute force solution, right?
Yeah.
So what was the time complexity of that? Can you just walk me through it?
Oh, so that would be like order n square. That's like basically comparing every node with every other node. So just store it in an array and then like traverse it in any which way, store it in an array and then compare every node with every other node. So for every ith node, I check the jth node, I check the value if it is equal to the target or not. That's n square. But what now I'm saying is that if we get the array and sort it and then like do this 2-pointer approach, then it will be order n. But sorting, okay,
So
no. So
now, yeah, go on. You
yeah,
were
like
saying
we
something.
don't even need to sort it. Like BST, if we do the in-order traversal, we'll get the sorted array automatically. So in order and time, I can traverse the array, like the binary search tree, and get it in order, like in a sorted array, and then apply the 2-pointer approach.
Okay, so you've basically converted this problem to finding a pair in a sorted array.
Yes.
Right. So, and with that approach, you are able to improve upon time from n square. You are able to reach n, but you are taking a hit on space, right?
Yes.
Because
Yes.
we'll be needing extra space for this.
Yes.
Okay. Okay. So, if I ask you, like, do you think we can further improve upon the space complexity? So, is there some BST property that's coming to your mind which you can utilize to bring down the space complexity?
So, like, we are doing an in-order traversal already, and okay. So, like, basically, what we are doing is like this 2-pointer approach. We basically know the leftmost node and we know the rightmost node, right? So, if you know the leftmost node and the rightmost node, we are just trying to make a switch from like where we have to go in the direction. So, if there is a way that I can do the two traversals together, wait, let me give it a thought. So, yeah, so basically like what I'm doing is like just to do the traversals, I'm storing it in an array. I'm thinking if there is a way that I can do the traversal together to find the, basically like in a sorted array, I'll get the least value and the max value and then decide where I have to move to the like a value greater than the least value or the value smaller than the max value. So yeah, so like okay. So basically in order traversal, we can always get the minimum value and then the next minimum and then the next minimum, right? So if we do some sort of a reverse in order, like instead of like calling from the left, if we start calling from the right, we'll get the maximum values on the right and the maximum values on the minimum values on the left. And then we can do the same comparison. And like instead of storing everything, we can decide like in which traversal we have to move forward. So for example, if we are at 1 and 7, and our target node was like say 8, right? No, let's say it's 6. So if you are at 1 at 7, the sum is 8. I have to move to 6. So what I'll do in my traversal itself is that I will move to the next node in my reverse in order traversal on the right.
Okay.
And if it's 9, I'll do the same again. No, sorry. Like if the value was 9, then I'll do it on the left. Like you get it. Like I can explain it.
I get your point. Yeah, I mean, I understand your working, but how will that work in terms of trees? Like you are saying that you will move from one to two, but how will you do that in terms of tree? Because there is no such like parent pointer or anything, right? So how will you access the nodes, the
Oh,
farthest nodes?
okay. So like I'll not use recursion. Like I was thinking like recursion will be like a little tricky to manage in this. So I was thinking of like some
Hmm.
iterative traversal in which like I
Okay.
reach to the leftmost node, and like
Hmm.
basically I'm doing like an iterative in order traversal. Like I reach to the leftmost node, and that is now
Okay.
my candidate. And then I decide what I have to do. Like let's take an example. For example, in this
Mhm.
case, I'll so basically to maintain a in order traversal, all we need is a stack, right? We don't need anything else.
Okay.
So basically, let's say I
Okay.
have a left stack, which will basically look like 4, 2, 1, and null. So that's how I push inside the stack. Okay.
Okay.
Then whenever I reach a null, I know that this is not the answer. This is not the leftmost minimum value, but I am sure that the leftmost minimum value is the top value of the stack. So basically,
Mhm.
I remove one. So now I know that I
Okay.
have a left candidate which is equals to 1, right?
Okay.
Similarly, I'll do on the right. So let's say you have a right stack which is like 4, 6, 7, and then you
Hmm.
encounter a null. Like we are pushing it in
Okay.
this way that we go to the right, push it, push it, push it. Then I know if I encountered a null that, oh no, this is not the value. 7 should be my right candidate. Okay.
Hmm.
So you say right candidate is equals to 7. Now, while this is going on, what I'll do is I'll check the values of 1 plus 7, left candidate plus right candidate. And my say target was 6. So this value is greater. So I can be sure that my right candidate is something that is causing the overflow. Like I need to move
Yeah.
in the closest possible way, and that will be possible if I move from the right candidate one node above. How will I do that? So basically, when I popped 7 out of my like stack, what I'll do is at the
Hmm.
same time, I'll move to the right node of stack and then start, oh, sorry, the left node of stack and keep pushing the right nodes inside it. So
Okay.
basically, what will happen, like let's think of a place where we somehow reach to 6.
Hmm.
So then
Okay.
how I'll go forward is that I would have processed like for some reason, let's say we have a right candidate equals to 6 and we have already processed 7 and that was no longer needed. So at 6, what I'll do is I'll pop 6 and at the same time I'll push 5 inside the stack by setting my right candidate to be 6.
Okay.
Okay. So now what will
Okay.
happen is in this 5, I'll keep pushing the right nodes of 5. So I've pushed 5.
Okay.
I'll push. So I'll go one level up, go to 5 and start pushing all the nodes on the right of 5. So that will be my
Hmm.
stack. And suppose 5 had like 3 nodes on the right, say like there is no scope for any other nodes, but like say
Hmm.
if they were not integers, you had like 5.1, 5.2, 5.3, 5.4, 5.5, like just for the sake of inserting in this
Yeah.
tree. I'll keep inserting them on the right of 5 because they will all be on the right of 5. So I'll infinitely
Hmm.
traverse till there is a right node and push that. So now my next
Yeah.
candidate on the right would be that node on the top of the stack.
Okay.
Yeah.
Yeah. I got your logic.
Yeah.
Okay. And similarly, how I'm assuming that for the left, you will just
Oh
go
yeah.
to the right and then keep pushing the left ones.
Yes. Yes. Exactly. Yeah.
Okay. Okay. And then how will you know when to stop?
Oh, okay. So basically, to know when to stop, like if I found a value, I can stop. If I didn't find a value at the end of the traversal, I can be like false. Nothing happens.
Okay.
Yeah.
Okay. And basically, programmatically, how will you decide that there is nothing to search for further? So, okay, if you found a match, it's all well and good. You
Yeah.
return true.
Yeah.
I'm just trying to understand when will you return false? Like, how will you decide that at this point I need to
Oh,
return false?
okay. 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 So basically, like we'll be maintaining like two traversals, right? So we'll just
Hmm.
check like if the candidate values matches. If yes, great. If not, then we like simply check is like any stack having a value. Like both the
Okay.
like left traversal and right traversal should have a value in them, right? So if there is no
Yeah,
value
correct.
in them, then we can be sure that, hey, let's return false. Like I can never find an
Okay.
answer.
Okay.
Yeah.
Yeah, this sounds okay. So in this case, what do you think the space complexity will be now? Since it is clear that you are definitely not storing the entire tree,
Yeah.
just some portions of it. So what will be the space complexity of
Oh,
this?
yes. So basically, like at any point, I am storing the depth of the tree at max. So that
Mm-hmm.
would be log n, like twice into log n, because like you're having two left traversal and right traversal, so 2 log n, which is basically log n.
Okay.
That will be the space
Yeah.
complexity.
So basically, it looks to me that like the maximum elements at any point of time can
Yeah,
be the height, but whatever will be the height of the tree, right?
yeah, 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 yeah.
Okay. So let's now talk about in the worst case, how much space you will be using if we
Oh,
are talking about the worst case. And what will
okay.
be the worst case if you can think of it?
Oh, yeah, yeah, yeah. So like the worst case will be having a skewed tree, like a left skewed tree or a right skewed tree where all the elements are stacked in like left node,
Mm,
left node, left node, or right node, right node, right node of the root. So that will be
okay.
here, since our complexity is not basically log n, it's order height, right? So that height will
Mm,
be n. So it's order n in worst
mm,
case, like average case, it's log n. So like if we have some sort of like a balanced tree, then we can say that
mm.
it's log n, otherwise it's order n.
Okay. So yeah, Varun, this solution sounds good to me.
Okay,
I'll give you the signature and then I'll ask you to write the code. Okay.
okay, okay.
So on the next sheet, I am writing the basically signature for this.
Oh, okay. I think this is. Oh, you're okay if I use C++, right? That's not a problem.
Yeah, that is fine.
Okay.
Since I am like mostly familiar with Java, that's why I'm writing the signature in that. So so this is what you'll get, and you need to return a Boolean value. Okay. Now you can modify it as per C++ if you want.
Okay. Okay. Let's do this then. Okay. So basically, firstly, what I need is like a struct node, which basically has int val or int
Mm-hmm.
data, as you call it, int data
Mm-hmm.
and node. Like, please excuse the auto capitalization that is happening.
Yeah, that's fine.
Left and star right. Then what you do is you define a Boolean function which pair exists, and we say you give me a node star root and int say target. Okay. So basically what we have to do now is, okay, so just give me a second. So I need to maintain 2 stacks to solve this problem. So let's maintain a left stack and a right stack. So
Okay.
let's basically the left stack will maintain your left traversal and your right stack will maintain your right traversal. So let's say you have a
Mm-hmm.
stack node star left traversal and you have another stack node star right traversal. Okay.
Okay.
Then what you need to do is like to initialize the stacks, what we can do is like we need to go to the left. Like what will happen in the starting? In the starting, I want the minimum value and the maximum value. Where will the minimum value
Correct.
be? Minimum value will be at the leftmost node of the tree, and the maximum value will be at the rightmost node of the tree. So let's initialize our
Okay.
stacks in such a way that um, that we have those values inside the stack. So we can say struct node star current is equals to root. Then we
Okay.
say while current, while we have a value in current, we'll simply keep pushing the values till in the left side in the left stack. So how we do that? We'll
Mm-hmm.
say that, sorry, your volume decreased. You'll say left traversal dot push. What will I push? I'll push current, and then I'll
Mm-hmm.
say current equals current's left. So that's how we like do for the left, and then
Mm-hmm.
similarly we'll do for the right. So while current is not
Okay.
equals to la, I'll say right traversal is equals to push current. Current is equals to currents right.
Okay.
Oh, sorry. Wait, I'll have to reinitialize my current.
Because it will become
Yeah,
null by that point.
yeah. So I'm pushing the values. So now basically what will happen is, like in the happy case, like I have some values in my left stack and my right stack, and the top of those values will basically be the respective left min and the right max. So like till we have some value in the stack, while right traversal not while not of right traversal dot, I don't remember this STL function. I think it's empty or is empty. Like, do I have to code that, or is
Okay.
it fine if I?
Okay, let's for now just assume that there is a function empty in the STL.
Yeah,
You can code as per that.
yeah. So if there is a value in the stack to consider, till there is a value in the stack to consider, is when we are like doing everything. So is the bracket matching? Yeah. So what you do now is no. Yeah. So basically what we need to do now is we need to check the values in the stack, right?
Okay.
How will we do that? So yeah, let's get the top values in the stack, and for that we'll say int left candidate is equals to, since the stacks are already not empty, we'll just pull out a candidate. So we'll say left traversal dot top,
Okay.
and similarly we can say sorry, right candidate is equals to right traversal dot top. So now we have our two values which are our candidates, right? Like I move to the leftmost, I move to the rightmost, I have the two values. Now
Okay.
I have to decide how do I move further in the stack. For that, first we'll compare these values and make a decision from which stack we need to like throw out the candidate. So for example, if it was 1 plus 7 and we had a target 6, we can be sure that 7 can never be our candidate. We can throw it out. So we can pop it out from the right stack. So let's think of that. So what you need over there is you just need to compare if left candidate plus right candidate is equal to target, oh sorry, is equal to target, then if this plus this is true, then what we need to do is we can be sure that we have found an answer, right? Yeah. So let's do that. Otherwise what do you mind if I move this to the next page?
No, that's fine.
Okay. Yeah, otherwise what I need to do is I need to make a decision that which value do I pop. So now there will be two cases in all, right? Else if something, wait, I'm just like ensuring the indentation is not messed up. Else if, yeah. So then what we can say is that if, yeah, if this thing, if this value is causing a problem, if you say that, yeah, if this plus left candidate,
Okay.
right? If this plus this is like, there are two cases, less than target or greater than target. Let's call this less than target. And similarly, we'll have a case where it's greater than target. So this is where we decide which stack to pursue forward, right? And how do we decide that? We'll simply remove. So now we are at a place where we are at a value less than the target. If we are at a value less than the target, what we need to do is we need to, so 1 plus 7 is less than 6. So then I need to increase my left, right?
Yeah.
So how do I do that? So I'll just say I'll pop from the left stack. That's it. So you say
Okay.
left stack dot pop, and what else do I need to do? So I have popped a value, but I need the node on the value also, right?
Mm-hmm.
Oh, okay. Sorry, my bad. So this should actually be a node because it's a
Since
stack of
it's
node.
a stack of nodes.
Yeah. So basically, I pop this value, and then I say that left candidate value or whatever
Hmm.
we had. Yeah, this and this. Like we can have another variables to store them, but for now we can say that like let's compare the
Hmm.
values. It's just a little messy, but we can. Yeah.
Yeah, it's fine, I think.
Yeah. So this is how we compare, and then we simply traverse. We simply pop the value, and while popping the value, now what I have to do is I know the node, right, which I had earlier.
Hmm.
So I can just change this node to, because now I'm sure that if I popped a value, I've traversed all the left part. I am done with the left tree. I just need to take a look at the right tree. So I say
Yep.
left candidates right,
Okay.
right? So this way, say if you are at a place where you are, if you look at the example above, for some reason we reached a 2, then I'm sure that I would have
Hmm.
processed 1 by now. So I have to from 2, and I'm processing 2. I have processed 2 now. This is how in-order traversal works. So 1 is done,
Yep.
root is done. Now process the right. How do I do the right? I'll go to the right, which is 3, and then I'll push
Hmm.
everything on the left of tree, on the left of 3 inside the stack now, like we did over
Okay.
here, like we did over here.
Hmm.
So we'll simply like do this part again, and how we'll do that is, yeah, while this left candidate is not equals null, I'll
Hmm.
simply push everything on the left of this right child. I'll simply push everything on the left of this right child in the left array, in the left traversal array, in the left traversal stack. So
Hmm.
left traversal dot push, and I'll push my left candidate, and I'll say that my left candidate, sorry, and my left candidate is equals to left candidates. We are going to the left, right? We keep going to the left. Yeah, it is left candidates left.
Okay.
Okay. And like similarly, like we don't, I think, need else if we just need else, because these are the only two cases that we'll have. So we
Hmm.
don't even need to check this. Else, like I'll just copy this part over here and just check like what else. So now I'll pop from the right candidate, sorry, the right array. I'll initialize my right candidate. And now what will happen is that if I'm popping from the right, I know that nothing on the right is useful to me. So I go to the left of that,
Okay.
and till my right candidate is not equals to null, I'll update my right traversal array and push the right candidate into it, because this has never been visited. And then I changed my right candidate to right candidates. Now we are going to the right of that. I'll just explain with an example. So for example, if you come to the
Hmm.
top, like if for some reason I reached 6, I'm sure that I don't want to go on 7. So in my stack, I'll push 5, and I'll push all the children on the right of 5. That will give me
Okay.
the maximum value that is closest to 7. And that is what we are
Hmm.
interested in this 2-pointer
Okay.
approach.
Yep.
So yeah, this will work fine, and then this will work, and then yeah, okay, it's done. So we have while, and at the end of this while, if we reach a point where there is nothing in the array, nothing left in the stack, I'll simply return false over here, and like we are returning
Hmm.
true over here. So yeah,
Okay. So, do you want to do a spot check before I take a look?
sure. So you take the left, then you go to the root, then you push everything in the left, then you push everything in the right, then you check if anything is there. If left candidate, left traversal dot top, right candidate, right traversal dot top. If right candidate's value plus left candidate's, oh, okay, sorry. I think I need one more check, like you pointed out. Oh, sorry. If this Like I cannot have the same node sum up twice.
Yep.
Uh,
And in this algorithm, I think it can happen that
yeah,
basically you are processing the same node in both the traversals.
yeah, it will happen because I'm having no check where like I stop if the value of the left is. So basically we are doing a traversal, right? Be it in order or reverse in order. Like we'll always come to all the nodes of the tree. So we need to
Yep,
reach to
correct.
a point that if the value is equal, then just throw out of the tree because we would have processed everything on the right and everything on the left. Sorry, just one sec. Then what you do is, okay, it's not working. The indentation is not working for some reason. Okay, yeah.
Okay, I think that is fine.
Yeah, if this and left candidate is, if they are equal, then it is wrong. But if they are not equal, then it is a true case. Right underscore candidate. And I check this over here. And for some reason, if they are equal, let the whole tree traverse. Like I can have one more check. Like if at any point left candidate is greater than right, I can return false. I can have all, like, so basically what will happen in this is like I'm still traversing the whole tree from both ends, right? So like we can have another check like at any point if left candidate is greater than right candidate, if left candidate is greater than right underscore candidate, I can be sure to return true. Like, yeah, like again, this will be values. But like, it's not like needed. Like we are not improving on the complexities.
Exactly. And also, should it be returned true or should it be
sorry.
returned false?
Sorry. This will be false. Yeah, this will be false.
Yeah. I mean, it's good to have, but
It's
in
not,
terms of complexity, it won't help much because it will still stay linear time only.
Yeah.
So,
Yeah.
Okay. So are you confident enough? Should I take a look now?
Yes, please.
Okay. Give me 2 minutes. Yeah, I think Varun, this code looks fine, and I think it will work fine also.
Cool.
So this
Thanks.
is all well and good.
Yeah.
So looks like you were also able to beat me also when the tables have turned.
I don't call it beating. We both were able to solve, so it's one all.
Yeah, thanks for giving me the credit. So
Yeah.
I also solved.
Yeah.
So I hope you guys enjoyed this video, and thanks for watching. We'll see you in the next one.
Cool. Thanks, guys. Bye.
For new programming updates and videos, subscribe to Coding Ninjas channel.